Hello, everyone. Welcome to the fourth session. We'll just continue the optimization that we've been talking about before and how this leads into sort of type stability. This is a feature you'll see in Julia specifically. So some of the things you'll hear today will basically only apply to Julia. Yeah, so we'll start with the live example from last time. Also, in case anyone wants to follow along with some of the live examples, all of the code is in this repository as well. And okay, so we were talking about allocations last time and how if you're making lots and lots of allocations on the heap, that can severely degrade your performance. And it's one of the big things to look out for when you're sort of trying to optimize your code, is making sure that you're not allocating or you're allocating as little as possible. So it's one of the major sort of bits to focus on when you're optimizing your code. So we have a function here which essentially just takes a vector of vectors, so basically a table of data, and just sort of writes this output, creates like a sort of CSV file. I assume everyone here will have seen CSV files before, but essentially you just have like a sort of Excel sort of spreadsheet where you have your data just separated by commas, like on a new line. And then usually, or sometimes you have headers like X, comma, Y. But you can think of it just like an Excel spreadsheet, but a more compressed format. So yeah, so all this does is it iterates over some rows of values and iterates through each column and basically builds up this string. So just like an array of characters, bit by bit. There's no headers though on this one. So it will just write the first number, then it will add a comma, write the second number, and when it gets to the end of the line, it will add a new line and sort of continue until the end. So in order to have a look at this, we'll just see what the performance of this is like to begin with. So if we have a look, our input rows is just a list or an array of vectors. They're all of the same size here as well. And then when we run our function and sort of imagine printing the output into a file, you get exactly what you would expect, just all of the values or all of the rows on a new line with a comma separating each of the columns. So just to begin with, we can sort of benchmark this code. It might take a second to actually run. More than a few seconds because it's not very optimized. Okay, so when we use this at benchmark function, and remember we give it the function name and the input, and we put this $sign in front for the sort of interpolation of the values. Hopefully, if I make this a bit bigger, it's easier to see. So yeah, I give you a spectrum of time, but you could see here that the distribution of the histogram is actually really wide. Like the minimum time was like 400 microseconds, and the maximum time was like 1.7 milliseconds. So this is one of the issues with allocating a lot of memory. You have a really variable time for the same code to execute. It's doing the same number of instructions, but the samples that are on the right-hand side, what would happen halfway through is the garbage collector has to stop the program and like clean up all of the excess allocations that you've made. So that's where you see quite a lot of values on this top side. If you were to benchmark it with at B time, it would only give you this 404 microseconds, so the fastest one. So it can be a bit misleading if you only use B time as opposed to like a full benchmark. Yes, so one of the other pieces of information it gives us is it says that it's allocating over 5,000 times, and you would wonder like where are these allocations coming from? Sometimes you don't know, especially if you're using someone else's code, you're not quite sure where the allocations actually are, and it's allocating 5 megabytes of memory, which isn't much, but in the context of this example, it can be quite a lot. And imagine you wanted to save some data to a file where you had millions and millions of examples. This would quickly explode, and be a huge slowdown. So the way we're going to actually investigate this is, instead of just looking at the source code, we'll go through the process of profiling. So in order to, profiling specifically for memory allocations. So this profile module is inbuilt into the Julia base library, but we're also using this pprof module as well, just for like visualizing the results. So the profiling is stateful, so you don't like save the result of the profiling into a variable. It has like a variable behind the scenes. So when you're doing this and you're doing it multiple times, just make sure you clear that sort of clear the results of your previous profile before you start running, or else it will like put them all together and the results you'll see are very confusing. So in the profile module, there's this allocs submodule inside that specifically profiles for allocations. So there is this @profile macro in the normal namespace, and that will do profiling based on time and speeds. But here we want to look for allocation specifically. The way it will do this is it will it will put code running while your code is running to stop and basically check what it's doing at each time step. So if you have a really long running piece of code, doing a profile of it will take far, far longer. And if you have lots and lots of allocations, checking every single line will take a lot of time. So you have this option to choose a sample rate, which basically, if you're allocating a lot, you can turn the sample rate way down and you'll get less accurate results, but it won't take as long to profile. And what you put on the right-hand side is just the function you want to profile, just as normal. And if we, so we run that, the profile didn't take that long. So we can move on to visualizing it. And again, we didn't pass in any variable to this. It just looks to see what the inbuilt profile module last profiled from here. So when you run this command, it will start a web server that basically is just like an interactive UI for exploring the data. So if you hold down Control and click on the link, it should open it in a web browser. Okay. Okay, this isn't showing anything so far. So let me just run this again. Clear. Okay, yeah. So sometimes it will take a while to just like analyze it and build up all of the visualizations, but this step shouldn't take too long. Okay, so when you click on the link, it gives you a few different views of the data. So you can view all of the sort of recursive function calls that are happening, and usually at the bottom is the most interesting stuff. This view is honestly not the most useful, and so what people usually use is I'll zoom in a bit, flame graph. So on the top left-hand side, you can change the view to a few different things, and the flame graph is usually the most interesting. And you might not be able to immediately see it, but you can highlight sections by searching. So we know our function was called serialize, and it highlights it in purple. And the width of these blocks tell you how many allocations were made by each of the function calls. And you can see there are two main function calls in here. One is called string, and the other is this times function. And I should say is when you concatenate arrays together in Julia. So I'll just open a new REPL to show you an example. I say concatenate arrays, concatenate strings. So if you want to join the string A and B, you do A times B. In other languages, they use the plus symbol. It's just a choice, but the sort of justification I've seen is if you concatenate A and B together, it's different from when you concatenate B and A. So they use times to show that it's different. Also, you can do other things like raising it to like the power of 10 to get multiple strings out of it. Okay, so these are the two main functions that are causing your allocations. And this is one view of it. So you can see the number of allocations, but you can also see the size. So in this top left-hand menu sample, you can change it to size, and you can see that the majority of the size of the allocations comes from this times operator. And you can't even really see it, but on this side is the string operator. And what the string operator does is just convert a number to a string. That's what it's doing in this code. So this view, again, is not the most helpful. So there's another view where you can see the source code, but there's a lot of different examples here. So you can just type in the name of your function at the search bar, hit enter, and it will show you your function, and it will highlight the exact lines where you've allocated memory. I'll zoom in a bit. So you can see that the majority of our allocations are coming from these two lines here. So adding commas and also adding the actual values itself. So converting the value to a string and appending that onto sort of your current output. So where you are currently in your string. So this is really nice, especially if you have like a big example with lots of functions and you can't actually you can't work out where the allocations are coming from. If you do a profile in this way, you can sort of scan through the source code and it will highlight the exact lines of where these allocations are coming from. So if we go back to the function and just stop that web server. So this was the example before, and we're using this star to append things. And if people have sort of programmed a lot with string manipulation in other languages, you know that concatenating strings is usually really terrible for performance. And so what people do instead is they create a buffer and then they write to the buffer. So the buffer will sort of reserve space for, let's say, like 1,000 characters. And while you're adding values to the string, it will only resize the arrays when you overflow that buffer. And then it will give you more room so you can allocate less often. It will still allocate a bit, but it's much more efficient. So we have, just to save some time, we have an equivalent implementation that uses this IO buffer. And instead of directly converting things to strings, we just print the values into the buffer and build up the string that way. So if anyone's done something like C# before, there's a class called string builder, which basically acts like this buffer as well. Most languages will have something like this because it's a really common optimization. And if we first clear the profile, also forgot to say, you should, before you profile, you should run the function first, because remember, the first time that you run a function, it gets compiled. And you don't want to profile the compilation process because that really won't tell you anything. So if you run it first, it'll get compiled, so it won't show up in your profiling results. So you profile it in the same way, and then run the visualization tool. Take a second, and I'll go straight to the source serialize function. You can see that these numbers are far lower than before. We were looking at the sizes. This is measured in kilobytes. Last time it was like around 5 megabytes in total. So this is what, 2 orders of magnitude fewer than the previous method. If we go back and actually benchmark this, you say the lowest one before was about 400 microseconds. This should be, yeah, so this is over 4 times faster, which is really nice. But the major point was the longest time in the previous example when you were allocating a lot was like 1.7 milliseconds, but the longest time here is only 110 microseconds. So that's much faster for a relatively simple change in your code. And you can imagine that if you're doing this operation or an operation in an inner loop, so you're doing it multiple times, then this sort of small optimization can save you like days in computing time. Okay, any questions about this? Yes.
Sorry, how are you getting those tick marks? That's coming from running each line. How do you do that?
Oh, right, the tick marks here. Yeah. So when you start the REPL in VS Code with this start REPL command, when you have a line of code, so like a = 5, if you press Control Enter, it will run it in the REPL.
Okay. a Jupyter notebook.
Like a Jupyter notebook, exactly. Yeah, it's quite helpful if you want to, because you technically could write all of your functions here, but it's not very nice to do it inside the REPL directly. So you can put it in your file and then directly send things to the REPL that way. Okay, all right, so that example is done. I'll cover a few things from last time as well. Let me just restart REPL just
when you run to the buffer, you don't need to manually clear it. You don't have to clean. Okay.
No, so the good thing about garbage collection is as soon as you stop using an item, the garbage collector will clean it up for you.
Okay, then, so in the code above, you have some allocation clear or something like that.
Right, the profile clear. That clears the results of the profiling. That's just to make sure, because I can show you what happens if you don't do this. So,
I don't quite understand what you got. What do you mean by profile in this case? I don't quite understand.
So the profiling is basically a way of running your code and then sampling to check what it's doing at certain times. So like profiling for speed will say how long is this piece of code spending in each of the functions.
Okay.
This one is a bit different. It's allocating, or it's profiling memory allocation. So every time it allocates, it samples whether, like how much it's allocating and also which lines are allocating.
I see. I see.
That makes sense?
Yes. Yes.
Okay. So the major difference between this and like benchmarking is benchmarking, you'd set up your data yourself and you'd have to do it line by line to see which ones are causing the poor performance, but profiling lets you sort of zoom out a bit and find the line instead of going through it one by one.
And I assume you had to run this profile before you run this pprof.
Yes, exactly. It's a bit confusing. It's kind of like a stateful C sort of thing. So as soon as you run a profile here, it saves it
Somewhere.
as like the current profile that it's looking at.
Okay.
Kind of like when you're like plotting in matplotlib and you use another command, it will add to the current plot.
Okay.
By default. It's the same sort of concept. Okay, is that all good? Great. Okay, so I'll move on to views. May or may not have come across these in other languages, but let's say we create a 4x4 array and we want to take just a slice of the array. Let's say the top left-hand corner of the 2x2. You can do that in Julia with basically just indexing with a range. So this will get the first two rows, and this specifies the first two columns as well. So when you do this, it actually creates a copy. No, it didn't execute the full line. Yeah, so it creates a copy and it selects these top two elements, so 74, 51, 16, 15, from this array. And this can be really useful for sort of writing your code in a nice way, because you can cut up your arrays and use them however you want. But this actually does a copy. So if we set b equal to 0, so now b is just a matrix of zeros, and we look at a again, a is completely unchanged. This is kind of what you expect by default. But the issue is here is when you've created that slice, you've created a new array, you've allocated new memory. So what people tend to do instead is create views. So there are a few different like syntaxes for how you can create a view. But the easiest way is if you're using your original syntax and you just put this @view macro on the front, it will create a view into that matrix, which is kind of like a pointer saying, look at this part of memory. Don't create a copy, just look at a different part of memory. If you look at C here, you can say, you can see up to now, it has the same elements in as B did previously. So acts in the same way. But if we set all of the elements equal to 0, so C is just zeros, and we look at the A matrix, it's set all of the elements equal to 0 in that matrix as well. So you've got to be a bit careful if you're creating a view and then modifying it, then it will modify your original data as well. Yeah, these are all nice. So you don't have to do just like contiguous blocks of memory. You can, for example, select every other item from a column. and set the values in there. So I've just set every other element in the third column equal to 1. And yeah, you can also do this with the sort of broadcasting notation as well. So if you create a slice on the left-hand side of the equals operator and you do sort of dot equals for element wise, you can, and print out A again, you can set only parts of your matrix equal to a certain value as well. And this won't allocate any memory. It will just create a view on the left-hand side and do the operation on the view. This next part basically just shows you that sometimes it's better to avoid creating the views because, so I'll just show you. So this function will add up all of the rows in a matrix and sort of return just like a column vector with the sum of each row in each element. Yeah. Question. Thank you. Julia was column first. Yeah, so I guess column first. So the first
should be row. The first index is row.
Yeah, let's have a look just to make sure. Okay, so the first number is okay, column major, not column first. If that there's a bit of distinction here. So you're essentially going down the matrix from the top left-hand side, and you go down the columns. So column major just means you're going down the columns for your indexing. So the first value is not the column, it's the row that you're in. So yeah, so A31 will give you the value 45 because it's in the third row and the first column. Yeah, sometimes you might just have to check in the REPL which one is which to make sure you're doing it the right way around. Does that answer the question? Yeah, cool. Okay, yeah, so we have this function that sums up all of the rows, and there's also a function inbuilt that does the sum. So essentially what this does is it loops over each row and creates a view that just slices the row out of the matrix and then sums that and then puts that in a different array. But if we benchmark both of these, might take a second. Doing this will not create a copy of the array, so the values that you're summing up won't be next to each other in memory. So it won't be very cache friendly. So what we should see is it's a lot slower than just creating copies of the array. Yeah, so you see, like if you're slicing up the array, let's say you have each row and you're selecting each value here. These values are not next to each other in memory because they have padding from all of the columns. So you don't have this sort of like nice cache-friendly, SIMD-friendly layout in memory. But if you were to actually create a copy with all of these values, then any operations you do on them will be in a sort of contiguous array. Everything will be cache-friendly and faster. So this example is just sometimes it's better to make an actual copy, but it will depend on your use case. Yeah, great. All right. Next one is we spoke about the sort of broadcasting notation and the sort of difference between them. Using algebra. Yeah, so we saw this before, that you can equivalently write a for loop with this dot equals notation. And so this will say, calculate element wise, A times the sign of B, and the dot equals here says store it in the array C. And so these two implementations, the broadcast and the F and the normal F with the for loop, are basically equivalent. They do exactly the same thing. The main reason why people use broadcasting is because you can essentially fuse your loop. So instead of doing calculating an array for the sign of B with each element, and then calculating A times the sign of that new array, you can just do it all at the same time, element-wise, and not have to allocate any new memory. Yeah, if we benchmark these, they should be basically the same, I hope. So we just see. Yeah, you can see they're essentially the same, like a bit different because the implementation is slightly different, but for all intents and purposes, they are pretty much identical. You can choose which one to use based on just what's easier to write. People use this sort of dot notation quite a lot because it will handle all of the sort of bounds checking and make sure the arrays are like the right size and shapes, which can make your code a bit easier to read and also a bit safer as well. So if you end up putting the wrong thing in, it will give you an error. That's also why we put this bounds check in, but again, it's a bit more verbose to do it this way. Okay, so this last example shows you how sort of powerful this sort of broadcast notation can be, or rather this is kind of like a map. So structs in Julia are like collections of like items. So instead of having to like pass in like parameter 1, parameter 2, parameter 3, parameter 4, you can sort of group them together into a struct, kind of like a class from other languages like Python, but they don't have any functions associated with them. They're just collections of data put together. So this struct has two fields. It has an A value, which is just a float, and it has a B value, which is a 1D vector of float values. So I have to define it first. So we can use this list comprehension. Has anyone seen these list comprehensions? They're really common in Python before. Okay, so it's just a clean syntax for doing things. Essentially, what you can do with this sort of map functionality is you can say for each element in this list, perform this operation in this anonymous function. So each element X, this is just whatever you've named the element in the list. This right arrow just means on the right hand side, this is the function to perform. And I'm just saying get the length of this vector that's stored in the B value of your struct. So if you perform this map, it will do this element-wise for each of these structs that you have involved.
So now my list is a list of lengths.
Yes, a list.
My list, right? My list originally is a list of structures. Now it's a list of numbers.
So it creates a map. So it maps from one list to a new list. This is a completely new array.
Okay.
Yeah. So my list is, if I have a look at it, my list is still there. Unfortunately, it doesn't look very nice. But if you look at like one element, you can see that it has this A value to begin with, and it has this B value. So you can say dot A to get that out and dot B to get the list out.
So what do you call this new array?
Nothing, it just returned it to the REPL. So equivalently, you can say, instead of using this map notation, it's basically the same as creating this anonymous function and then broadcasting it onto your list. This is two ways of writing the exact same thing. So if we write this out, we get the same response. And if I just show you quickly, this is just an anonymous function. And so it gives it a sort of number, and it just says it's a function. So in Julia, functions are objects as well as like types and things. So you can pass functions around into different functions and work on it that way. Is that all clear? Okay. So the next example, we spoke about sometimes using the array notation is quite nice for expressing your code, but it has this sort of performance penalty, and it's particularly bad when you're doing lots of very small allocations. So an alternative to this is using the static arrays package, which does just that. It says it allows you to create arrays which have a fixed size, so that you can't change the size of them after they're created, and they also have fixed types as well. And basically what this means is if it's a fixed size, then the compiler can stack allocate them instead of heap allocating them. So stack allocations tend to be much faster. So we've got this function that just works out the cross product between two three-dimensional vectors and puts them in a new array. So if we create two vectors, A and B, we can sort of benchmark how long it takes to work out a vector that's a cross product. And you see here you've got one allocation because you have to allocate the output array. And this takes about 20 nanoseconds. So it's not that bad, but if you're doing lots of these small operations inside a loop, that extra time can really add up. So the only real difference with using these static vectors is it has a different type. So before, the type was a vector, whereas what we're actually wanting to use is an S vector, so a static vector in this case. So this function definition basically just means it's got the same name, so it uses this if your inputs aren't static vectors. But if your inputs are static vectors, it will use this function instead. And this function, essentially, it's the same notation. It just, you pass it into this S vector. There's also this notation, which you'll see quite a lot, which instead of having to pass it to the constructor, like automatically, you can basically just put @S vector on the front of whatever vector you're creating.
This steer, we have to steer, if we use this macro, the macro like X vector, then still we have to use this using static.
Yeah, so this static arrays is called like exports these macros, so you can only use them once you've used that static array. So you have to add it to your package, like install it and use it.
You mean it's not mutable or something like that?
Yeah, so static means the size can't change, so you can't add or remove elements, but also
the elements within this array.
Yeah, so you can't change the elements either. So you can use syntax that makes it seem like you're mutating the argument, but what it's actually doing is creating an entirely new array and storing the result there instead.
Sorry, just to be clear, so you can't change the size and you can't change the elements inside.
Yes. Also, the size needs to be known at compile time. So if we look at the type of this A array, you can see that in the type, all it tells you is it's a vector, so that's just a one-dimensional array of float 64s. It tells you nothing about the sizes because arrays by default are or can be dynamically sized. So you can add elements or remove elements. So there's no information in the type that tells you how big it is. So you need to essentially specify that to the compiler. So you can't use this when you have a variable value. There are some ways around it, but they're written in the lecture notes, but I won't go over it here. Specifically here, we're saying there are 3 values because we've like physically typed out 3 values. And so it will know that there will never be more than that. And it also knows the type of these values from the types A and B that come in as well. This is the same function. To create a static array, you can just sort of pass in the values from your old array into the static or the S vector constructor. Does anyone know what these 3 dots do or what they're called, the operator? Yeah. Yeah, exactly. It expands the elements out. So if you have 3 elements like A, B, and C, and I'll put an example on the board. So imagine you have a function. So you have a function that takes in 3 parameters, A, B, and C, and you have these parameters in an array. I'll just call them 1, 2, and 3. Instead of having to write, let's call that array ARR. Instead of having to call that function, like my function, open brackets, usually you would have to write a of 1, comma, array of 2, etc., etc. What you can do instead is just write ARR dot dot dot, which will sort of expand the list out. This is called the splat operator. That is apparently the official name. And there's also another place where you'll see it is if, for example, you wanted to do the reverse of this. So let's say here, instead of A, B, and C, you want to take in an array, but you want to call it with values of A, B, and C, separated out with commas. You would write this function a dot dot dot, and this is called the slurp operator. So it's splat and slurp, and that will slurp up all of the values from your arguments into an array. Yeah. Great. Yeah, it's like the var args in Python, and also a lot of other languages have some implementation of this, but yeah, this is used quite a lot because it's quite convenient to write functions this way. And yeah, so this is just me being lazy instead of A1, A2, A3, essentially.
So when you call this function calls, why you put this dollar sign on it?
This is because it's benchmarking. If you were calling it normally, you don't put the bench. That's the only difference. If we benchmark this, you can see it's about 10 times faster, and it doesn't allocate at all as well. And the one nice thing about these, this sort of S vector, it's like you were writing out the components by hand. So like X equals this, Y equals this, Z equals this. So it just cleans up your code. So this is something you can use to make your code more readable, more friendly to look at, while also being very performant as well. Yes?
So if I make a static vector of 3 different things that are saved in memory, does it create new memory, or is it just point to?
It allocates it on the stack, so it doesn't do any heap allocations at all.
If I did like S vector of A, B, and C, it would create a copy of A.
Yeah, so it will just push it onto the stack. So usually your like if your functions sort of use the values when it gets compiled, a lot of this sort of vector will get compiled away and only sort of push the values into registers and things. So sometimes it doesn't even touch memory. Like main memory, it just goes straight into the registers and the machine instructions. Yeah.
So it knows to use the static vector cross function because you got the cross a colon S vector.
Yeah,
Right.
so that's something we'll talk about in a minute. Yeah, so this is part of Julia's type system, which makes it really sort of flexible, but also you can optimize for performance when you want to. That's probably, let me just check. Yeah, that's exactly what we're going to talk about now. Okay, so Julia has what's called multiple dispatch. Yeah, dispatch just means choosing which method to run. So you see in our previous example, we had 2 methods with the same name. So the function is cross, and the 2 methods are the 2 different implementations. And so most languages use single dispatch. So for example, if you're writing a class in Python, you'll have the first argument be self, and then you'll refer to self to access all of the values stored in that class. That's called single dispatch. So all of your functions live with the single type. Multiple dispatch basically just means the function doesn't belong to any specific type, and you don't prioritize one type over another. So it'll specialize on the types of all of the input arguments. So instead of having an integer with like an add method, the add method for the integer doesn't live inside like the integer definition. It lives external to that. And that means, and that makes a lot of sense for when you're adding like an integer to a float. It's like, what does it belong to, the float or the integer? multiple dispatch doesn't care. You just put the function definition away from your type definitions. This has a lot of advantages. Like people talk about like how well Julia sort of integrates lots of different packages from loads of different ecosystems together. I have an example on this on the new slide. There's also this talk about multiple dispatch by one of the main people involved with the Julia language, which people point to a lot in case you're interested. But the main thing with Julia is you can sort of specialize on the types. So that means you can generate the right machine code based on the types that you're using, but you can also be really flexible as well. There are some disadvantages to it though. So like finding which functions to use because they're not with the types can be a bit more difficult. And also what's really nice in Python is if you have an object and you press dot, the sort of autocomplete IntelliSense will show you every method that's associated with that, which is quite nice for a productivity reason, but Julia has a bigger problem with that.
I'm sorry, Jamie, what's glue code?
So I know, for example, if you have a package in Python, so like take matplotlib, for example. Matplotlib knows how to sort of plot values in a graph, and you have NumPy, which knows how to deal with arrays. You have to write some glue code to get NumPy values to be able to be passed into the matplotlib code for it to actually work. So you have to write this, I call it glue code. It's like an interface to say, when you get a NumPy array, do this special function instead. This is common everywhere. It's why most packages aren't really compatible with each other. You can't just like pass types from a package into another package that it doesn't know about before writing. Okay, so there's an example of this. Sorry about the quality of the screenshots from the talk, if you want to go into it. So one of Julia's biggest ecosystems is differential equations. It has probably like state-of-the-art differential equation solvers. Yeah, they are state-of-the-art. They're some of the fastest that you can get your hands on at the moment. But the creator basically just wanted to have uncertainties on this differential equation solver. It's all written in Julia. All he did was add this measurements package, which basically creates new number types that allow you to put uncertainties on your numbers. And it defines functions for if you add two numbers with uncertainties together, how do you propagate that error forwards? If you multiply them, how do you propagate the error forwards? So it's not a huge package, just a bit of code to make sure that you can propagate errors properly. All he did was change the input types to his functions, and he gets error bars out on his graph. There's no code specially written to take your differential equation package and make it compatible with your measurements. It just works. This is a really good example. It doesn't always work, but this is one of the main examples. Another big example from the Julia ecosystem is there's a package called CUDA, which allows you to create GPU arrays, which we'll see later on in the course. A lot of packages are compatible with using GPU arrays, even though they weren't written for GPUs in mind, just because they use generic sort of multiply operations and just deal with code using like the broadcast notation. There are some limitations in that, which we'll come to, but yeah, that's the sort of main point. And the way it does this is through its type system. So this kind of looks like a type inheritance tree. Some of you may have seen inheritance before from other languages. It's quite different from how other languages do inheritance. So a type can only inherit from something if it is an abstract type. And these abstract types define behavior. So for example, if you have some function and you want it to only work with numbers, not like characters or strings, you can restrict it so that it will only work with types that inherit from this number class. You can see this sort of on the top left hand side here. And again, you can further sort of restrict that ability and say, I only want this to work with real numbers, not complex numbers. It's not, some operations, I guess, aren't defined for complex numbers and are for real numbers. So you can make these distinctions based on how these types actually behave. All objects are what we call concrete types. concrete types just mean they are some existing data and they're on the bottom of these tree diagrams. So they're always the leaf nodes. So so these concrete types are final. So in other languages, you can define your sort of superclass and it has a bunch of data and properties associated with it. And you can define a new class that inherits from it and it will take all of those properties and put it in the new class. In Julia, you can't have that at all. All concrete types, you have to like duplicate the properties yourself. They're always final. There's no inheritance on that point. And the way that the multiple dispatch system works is it looks at all of the types of your arguments, if it has access to the type information, which it should, and it will choose the method which has the most specific implementation. By most specific, it just means lowest down on this tree. So for example, if you have a function definition that is defined for, a method that is defined for real inputs and a method that is defined for integers, the integer method will be chosen if you have an integer because that's a more specific value. It's more specific down the tree. This is useful because you can define your methods with these sort of abstract types and say this should work with these abstract types. And then you can extend the behavior. So you can create a new concrete type and pass it in. And if it implements the same interface and sort of behaves like this abstract type, you should be able to use it there. So the example in the CUDA package is it implements the abstract array interface. So how do you add two things together? How do you broadcast onto the array? How do you iterate through it, like the sizes and things like that? And that lets it be used in like eigenvalue problems and stuff down the line without changing too much of the code. This, you don't have to know in too much detail. It's something you get used to with practice. So I'll go through some of the practice. So I'll go through some of the type system. So I'll restart this. Okay, so one common item that people use in like machine learning is the concept of this one-hot vector. And essentially, if you have a vector of size n, a one-hot vector is all zeros and 1, 1. And that 1 can be anywhere in the vector. But essentially, you can implement it by keeping track of what's the length of this vector and also which is the index, which is the value of 1, because you only have one of them. It's like a special type of like a sparse array. You can implement what's called an interface, which is just a set of functions that your type will work on. So in the base library, there's this one called size. So if you say size of a vector, it will give you a tuple with the dimensions of your vector. And you can also implement this getIndex function. And basically what this means is, so let's create a one-hot vector with length 10, and the value at 3 is the one that's occupied. I'll just call this A for now. It's not liking this at all. Yeah, okay. I just didn't run it. So there, it knows how to treat it like a vector because you've defined these interface functions. So that basically means if you say A of 8, it knows that will be false, which is just a 0. And that's because we've defined this getIndex thing. So you can define your own array types and implement this getIndex function to basically treat it like an array. So all code that works with arrays will now work with your new type as well. So an example of this is I've created a function which just works out the dot product between two vectors. This is pretty standard, but I've restricted it to say that this can only work on types that inherit from this abstract array, sort of abstract type. In Julia, pretty much all abstract types begin with the word abstract. There are a few exceptions like number, which is also an abstract type. Also, when we defined our struct, we said that this struct inherits from this abstract vector. And we've also given it a type, saying the element types are bools, so true or false. This set of zeros, so like a less than sign and a colon, is like the inheritance operator. So for example, you can see whether the type int inherits from the type real, and this is just an evaluation. So true or false, does this happen? And you can compare whatever types here, saying does int inherit from float? This is also saying is int more specific than whatever is on the right. So if we were to say real and int in that direction, it would say false, because real is not more specific than an integer. So yeah.
If you went like a few steps up the tree there, would it still work?
Yeah. So you can, so for example, any is the supertype of everything. So if, remember before we had this function that we could treat as a type. So this is just a generic function. And if we say type of A, it's just the name of the function. And we can compare that to any, which should be true. So even functions inherit from this any type. Functions are kind of special as they're all concrete types, and they all inherit from this function abstract type as well. Yeah, so you can say int, or is it a subtype of any, and that will be true for anything. To answer. Cool. So what we'll do is we'll just create some random arrays and benchmark run our function first. So yeah, when you try and run a function that doesn't exist, it will tell you it's not defined. Okay, so we run our function. It takes about 1.6 sort of microseconds normally. We can create our one-hot vector like normal, and our implementation, we didn't change it at all. So this is still the same implementation that just works with abstract arrays. And you can see that it still takes about 1.6 microseconds, even though a dot product between a one-hot vector and a normal vector just selects the one value from your dense vector.
I assume in this function, this bounce check the size of A and B are the same.
Yeah, exactly. This is just a macro to make the test a bit simpler to write, but if you were to put in a vector with a different size, it would throw an error. That's what the bounds check does. And it basically gives you leeway to write this inbounds later to turn off the bounds checking, because you pay the price once at the beginning, and you don't have to do it for all elements in the array. Okay, so what we can do is we can write a specialized implementation of this same function. So we give it the same name, and the only thing that's changed is we say, well, if B is a one-hot vector, then do this implementation. And because one-hot vector is a concrete type, this should be the most specific implementation. So again, here we do a bounds check, but this basically just selects the element in A given by the index of the one-hot vector. So the index is where the one value is. If we implement this, the second function just sort of swaps the arguments around, because a dot product is commutative. You can put it whatever way around you want. If we run the benchmark for this, you can see that you've gone from like 1.6 microseconds down to 2 nanoseconds, because you're just reading one value from memory instead of having to do every single element. And so this is one of the ways in which like sparse arrays in general are implemented, is you only iterate over the non-zero values, like when you're doing like a sum or a product or something. Okay, that will make sense.
Does the bounds check only ever check the size function, or can you like define it? So if you have your own mid struct, could you define how to like compare them?
Yeah, I guess you could. So there's a macro called macro expand, which tells you what a macro does, which is nice. But if we actually have a look, yeah, so basically this just calls the bounds check function. So yeah, if you're in the REPL and you type a question mark, it will come up with the help. So if you don't know what function you want, let's say you're looking for like a product, you can type part of it and it will give you examples of functions that you can use. But if we have a look at bounds check, oh, okay, I don't know where it is. There'll be a function somewhere along the way that you can find to overload it. But in this case, you don't need to, right? Because you've implemented this base.size of your array. So you would implement that function instead.
Yeah, I'm just thinking if you have like multiple parameters in something where you can't, like the size defines it, but then you also have some other thing and you want to compare.
Well, this is a function, right? So you can, oh, right, as in, yeah, I guess I see what you mean. You don't have to write this at bounds check yourself. You can just write your own function and call that instead. The main benefit of using this at bounds check here is if you're using inbounds later on, it will turn off all of those checks for you. So this will get compiled away into, yeah, it just won't happen, this check. Okay, so that's a brief overview of the type system, but we'll show you what can go wrong when you sort of write your code in not the exact correct way. So again, I'll restart just to make sure. So we've got this function, which you think would be quite simple, right? You're just adding up values in an array and storing it in this variable s and outputting it. And then we have this other function, which just applies this sum element-wise. So if you have a vector of vectors, it will work out the sum of the inner rows and then the sum of that together. So if we have this sort of big array, which if we just show the first 10 elements, so this is just a vector of vectors. If we, sorry. Yeah, so if we benchmark this, no obvious issues will come out at all. So by all of our previous metrics, we see that, oh, it's not allocating that much memory, and you see it's pretty fast. Like you might, this sort of performance issue might just pass under the radar, but there is actually a problem with this code. And the way that we can see this is checking for type stability. So can the compiler actually work out what all of the types of the variables are throughout all of the functions and all of the nested functions as well? So there's a handy macro for this called @code1type, and you just give it your function that you want to check with the input that you want to check it with. And @code1type will highlight what it thinks the output type will be. So body is just what the function will return. And highlighted here, it says it's a union of float 64 and int 64. And a union just means it can be either of these types. So it doesn't actually know whether it's going to output a float or an int at compile time. So that's a bit of an issue. It's probably not inside this calc summary function. It's probably within this example function. So we'll do the same macro, but instead we'll call the example function with just one element of this vector of vectors. And you can see here, it says that S is either float 64 or int 64. So if you have a type stability nested inside a function, that usually propagates out to your outer functions. And so it says here, our variable S is either float or int. And also, because we're returning S, it's either float or int inside. Anyone have any reason why it might be an int and why it can't work out that it will be a float value based on this function?
S is initialized.
Yeah, exactly. And then when it goes, if there are elements in the loop, S will change types because Julia is dynamically typed just to let your code actually run. So you're allowed to change the type. But when you add an int and a float together, it will convert the result to a float. This is called promotion. So there's a function called promote type, or promote types, which basically gives you a bunch of examples. But if you add together two values or multiply two values, it will use this to work out what the return type is afterwards.
So this warning, this union float as an integer just tells me that this S can be either float or integer.
Yeah, exactly. And the reason it's highlighted in red is because usually this is a performance bug.
Okay, so usually to avoid any bugs, I just want either float or integer.
Yeah, you want one.
Favor a union.
Yeah, you want to avoid unions if possible. Up until like in Julia 1.8, 1.9, they added a lot of functionality called union splitting, which basically lets the compiler still produce quite optimal code, even with these unions, as long as there are only like maximum 3 different types it can be. As soon as it gets to more than that, or at worst, an abstract type. So for example, this could be, if this was of the any type, then it will have no chance of compiling any sort of optimal code for it at all. But yeah, basically, this is more performant than it used to be. The compiler will help you out a lot more. It's got a bit smarter over time, but it's still a big performance hit. So the way you sort of get around this is by you use like generic functions or generic typing. So instead of saying equals 0 here, you say, I want this to be 0 and of the type that's the same element type as your input array X. So this can be a bit more verbose in a way, but this is one way of doing it. And there are other functions as well, like 1, for example. So if you say 1 of like float 64, that will just compile to just the 1 as a constant. So there's no cost of like calling these functions because it can infer them at compile time. And we saw that all of the constant propagation will happen. So the compiler doesn't actually like call these functions. It will just replace it with whatever value is there. So yeah, if you're writing sort of generic code to work with any types, I'd recommend these functions 0 and also 1. There's also, you can use the promote type directly. So for example, you can say you want to promote either an integer or the element type of this X array, and that will choose whichever's bigger, an int 64, because that's what int is just alias to, or the element type of your array. But for most applications, this 0 function is your best bet.
Read the type of X. So this L type, what does it return?
So L type stands for element type. So for example, here we have, let's say, just one row of our vector. So the type is a vector containing float 64s, and this is known at compile time. And so L type function. So for example, I can write one here. So my L type, and we say our input is, I'll just call it array. It doesn't really matter what the name is for this. And we want to say a vector of, I'm going to say type T here. This is called generics, which we'll go on to in a second. So yeah, so you can write function definitions like this. So it's a vector of something, some generic type T, just something. And this where clause like captures what that is. So you can, for example, like print what that type is. So in the case of this vector float 32, that float 64, that T will become float 64. So I'm just going to let it return T here. And we can call this my L type of rows of 1. And it will return what the element type is. So this float 64.
So in this case, actually, in this example, F stable, so this S equals 0 type of X also works. Because
type of X is an array. So the type, so yeah, so the type of
X, because in our case, X is
X is an array, or it's a
Oh,
vector
okay,
of floats.
okay.
Yeah, so in that case,
Size and numbers.
the type of is different from the element type.
I see.
So yeah, there are some ways you can do this. So for example, you could write it to be a vector of some type t, capture this t variable, and instead of saying L type, you can just directly put t here. And anything you capture here will be compile time constants and within the type. So because they're constants, the compiler can sort of optimize a lot of it away. So a nice example of this is if you write a function that takes in some value a, and you want to do different things based on the type. So like if a is an integer, then you want to print hello. Otherwise, actually, just so it's easier, just return 1. Otherwise, if a is a float, return 2, else return 3. So you have these 3 options, and you see before I was talking about if loops are not very performant, but if the if loop is based on compile time information, so you know what the type of A is, then it can compile away all of the branches that will never be called. So if we have a look at this function, code typed, calling this my function with the value 1, which is an integer, it compiles away all of the if loop to just return whatever value is in the thing there. And again, if we convert that to a float, sorry, I wrote that incorrectly. Yeah, so if it goes to a float, it will just return this 2 value out of it as well. And then any other value you put in there, like low, it will return 3. These nothings get compiled away when it gets the LLVM compiler. This is quite nice because you can sort of trick the compiler to pass in compile time constants, by which I mean values that you have said are constant, to basically let your code do different things based on what values there are. So there's this type in Julia called the val type, or it's called a singleton type. So you can pass in some value, some constant, so let's say 5, and that will get encoded into the type information. So these curly brackets are the type information there. And so you can use that 5 as a constant in your code. So it's like, if this is 5, do one thing. If it's not 5, do a different thing. Okay. All right, does that make sense? I don't think we actually benchmarked the difference between these, so I'll just do that very quickly. So that was 32 microseconds. So hopefully this one, or our original one, will be slower. Yeah, it's about the same. Oh, right, because they're calling the same method. Yeah. So if we call this 2. Well, I'll look into that later. There's a whole example in the book that goes through all of this type stability, but I have one more thing to talk about, is containers. So containers are like arrays or structs or something that contains a value, and if you don't have the right type information there, it can sort of lead into issues. So this is a really common pattern you'll see, is someone just creates an empty array and then they'll push a bunch of values into it. So if we create this function f and look at what comes out of it, it says this is a vector of any type. So it has no idea of what goes in and or what is actually contained within that. So if this goes into a function, it won't know that it's got integers and floats in there. It will only know that they're of type any. So it won't be able to specialize on anything inside there. Sorry, it's taking a while. So you want to avoid that if possible. So when you're creating empty arrays, you can specify the type on the front yourself. which is what I do in the second example. Also, when you're creating structs, if you want it to be, if you want to restrict your types, instead of saying you want it to be abstract float like you would in a method, it's much better to use this syntax instead. So you want it to be a parametric type that restricts the parameter t to be a floating point type. So the way this works is if you say 2 and you put in like a normal float value, this float information will be in the type of the object, and so the compiler can specialize on it. If not, or you can pass in a different type, so this is a float 32, and that will also be in the type information there. All right, I'll leave everything there. Are there any questions on that in particular? This is just something to be careful of. Just one final thing. There's a whole section in the manual on performance tips. I'd recommend just reading through all of these. A lot of the examples are pretty similar to what I've gone on about, but if you're ever experiencing bad performance, the solution is probably inside of this document. Okay. Anything to ask? No? Great. Cool. So yeah,
There's a question in Teams.
I think that might be from something else. So yeah, there's the link to the GitHub repository. It's also on the website as well. Yeah, so there's links to all of the GitHub assignments there, and also the lecture videos. I'll put this one up after as well. Great, so have a nice evening, everyone. Thanks for staying so long. Sorry it went over a little bit.